web meeting this afternoon for the Volume and Turning Movement Project Steering Committee. We're pleased that everyone could join us. This is Joanna Rico from KMJ Consulting. Denise Markow will be joining in a few moments, and she has asked that we move things along because we have a lot of information to cover, and we want to make sure that we have an opportunity to get through it and that folks are able to ask questions. Just a few housekeeping items. If you're having difficulty with either the audio or the web, you can reach Justin at 484-557-7009. This is a relatively small group, and as such, we'd like to have this virtual meeting experience, and we're asking you to keep your phones muted until you are asking a question or speaking. You can do that by pressing *6 or using the mute/unmute feature on your phone. Speakers will answer the questions at the end of their presentations, and the materials will be available on the Coalition website following this meeting. The audio from this meeting is being recorded. Thanks to the agencies who have registered. If you are from an agency that's not listed, if you can give a shout out right now and let us know so that we make sure that we have our attendees represented accurately. Okay. And our speakers for today, we're going to start out with Stan Young from NREL, and then have Kaveh Sadabadi from UMD CATT, and also Yi Hao from NREL. And as I mentioned, Denise will be joining us. Again, please, at this point, if you can confirm that your line is muted. And we're going to get started with Stan, who's going to give us a project status update.
Hey, good morning, Joanne. Good morning, everyone. Is the volume adequate? Can you hear me well?
Could be just a little louder and it would be great.
Okay. Is that better?
Yeah, that's good.
Okay. To start off, typically we have these meetings every 3 to 4 months, and it's the steering committee. A couple of things have changed this time around. One is our steering committee got quite a bit larger. I know several online that may be online for the first time, and we would like to welcome you. We always invite interest in what we're doing. The other thing that happened is when we established the date for this steering committee meeting, we had 3 analysis activities in the works, and we were hoping one of those 3 would cross the finish line in time. As it turned out, all 3 have. So we're going to present all 3 of them as thoroughly as we can in the time limits possible. For those who have joined prior to this, we won't be going as deep into the detail, though we will be thorough, trying to save as much time for discussion. Anything that we present here will be available with slides, and trust me, there's probably twice the number of slides as what you'll see today, and I encourage all the speakers to keep that level of detail for anyone who wishes to get to that depth. Similarly, I usually start off with a review of where we've been and where we're going, and it will be abbreviated today. But I did want to put the project goal up. This started visioned 3 or 4 years ago when we were getting accustomed to getting high-quality travel time and speed throughout source probe data. And we're saying the time is coming when we should be able to estimate volume as well. And we put together this project with the project goal of to accelerate the time frame to a viable volume and turning movement data feed. Anywhere, anytime on the network, archive in real time, freeway and non-freeway, to ensure the initial data products meet members' information needs for operations, performance measures, and planning. And that's a high-level, broad view. I think we've accomplished much of that. I highlighted the non-freeway portion today because that is the emphasis or the common theme among all 3 presentations, even though they all 3 differ by a little bit. This is the general layout that we've followed. We're coming to completion. We're probably 75% through. As everything played out, we have 2 teams that are working on analysis, University of Maryland and my lab here at National Renewable Energy Lab. We're working with data sets available from NREX as well as TomTom. We're also collaborating with HERE and Streetlight Data. Both of them have contributed samples of their data to the project, though we have not gone as far in depth in analysis as we have with the other 2. We've created a calibration validation test bed and we hope to get to the products listed on the right. And we have several examples of how we've crossed the finish lines in many of these analysis. This is probably my favorite slide. In trying to explain this concept of what we're trying to do, I think the best description is a volume estimator. And in creating a volume estimator, we're using existing data, the network of ATRs and the network of 48-hour counts as base stations in an analogy of geolocation with GPS. And these ATRs in 48 hours, they help us calibrate our estimate when we're using machine learning, and ultimately they're our source for determining how accurate this process is. And so through that we expand the network of finite number of ATRs and 48-hour counts to the ubiquitous network across any state. We do use a variety of data, but probe data is key. This is the number of probe vehicles observed, but there is another a host of other inputs. And just to stress, and I think the word's getting out, where we don't intend to replace the network of high-quality sensors. What we tend to do is complement them and extend both in time and in space quality volume estimates. How good is good enough? This is a first attempt to bring a lot of things together. It's kind of, you're not going to be able to get this fully referenced in literature, but it's the collective thought of everyone working on this project. We have input from TTI, Sean Turner. We have input from many other people. How good is good enough? You're going to hear a lot of accuracy terms in these presentations. Error to capacity, error to max flow, mean absolute percentage error. The first two, error to capacity, is how much is the average error versus how much the road can carry. A lot of times it's hard to figure capacity, so instead of doing capacity, we just do maximum observed flow. So the two are quite closely related and can be directly compared for the most part. And our early surveys in the coalition says, you know, if you can get within 10%, the data is going to start to become useful. And the more we work at it, the more we say, you know, 5% or less is a really good target to reach. Once you get 5% or less, you really enable a lot of applications. From another point of view, this mean absolute percentage error, an error that's used many times in traffic engineering, it is very volume dependent. Not only are the accuracies we're seeing from this process volume dependent, but the requirements for accuracy is very volume dependent. You'll see a chart at the right that came out of some work at MnDOT related to estimating AADTs. And if you look at it and just see the trend, the lower the AADT, the higher the acceptable percent change, or the higher the acceptable variance. And we're trying to translate that into a language when we're creating this volume estimator of what is acceptable and what will work well. And we're narrowing down into some categories. I put 10 to 15% for high volume situations, 20 to 25 for mid, and 30 to 50 for low volumes. And once you get into low and extremely low volumes, you might have to change your metric from mean absolute error to actually mean absolute error. Well, I'll let you get into that. That's a bit more complicated than I want to share. But this is a first stab at it, and one of the things we're refining in order to get to a common discussion, trying to set that expectation across many applications. I thought I skipped a slide here. Today's agenda, that's the background I wanted to set. We're going to have three presentations over the next hour. The first one will be to look at Colorado estimates of volume once we get off the freeway. Venu and Yi will be presenting that. After that, University of Maryland, Kaveh will get on. They have the first results from processing all of Florida. Now, Florida does include freeways, but the Florida network also includes a lot of lower class roadways as well, so that's a common theme. And lastly, as time allows, we were able to do some first estimates of AADT. It's really a different way of thought. Most of the work and analysis work done to date has been kind of point in time, as if to support operations in real time, and we step back to see if we can adapt some of these processes for AADT estimates. And with that, I'm going to yield the remaining of the time to get these presentations started and turn it over to Venu and to Yi from NREL. And I think we have to have time to change the slide deck. So if you want to do that, Joanne, I'll hand off the mic.
Okay.
Give me 1 minute, and I'll promote Yi, and then we'll be good to go.
Okay.
He's there. Good. Thank you.
Okay. So, Sam, so Venu and I are going to present the current work that have been done by NREL on the volume estimation on lower class function roads. So, okay. So this is the structure of the presentation today. We're going to refresh the memories on why we are doing this and what we have done on this in this study. And then we're going to talk about the hourly volume estimation on lower functional class roads. Then we'll come to the summary and the conclusion. So let's Venu to talk about the motivations and the previous studies in this study.
Hi all. Kind of setting the stage for why we are doing all of this work. When looking at traffic sensors for any given city or region, typically they cover about 5 to 10%. Yi and I have debates on this. Yi is like it's more like 1 to 5%, and like I'm siding with the cities on this. We have about 10% observability of traffic volumes on road segments in a given city. So what happens to the remaining 90 to 95? Well, there are aggregate estimates like AADT and such, but there is no real-time or really disaggregate observability of volume information across different times of the day or different days of the week, or for any special events such as something like a snowstorm or something like a football game or along those lines. So the thought behind this project is, with increasing availability of probe vehicle data, is there a way we can combine information existing automated traffic volume recorders, ATRs, in any city, combine that with probe vehicle information to come up with a methodology to predict volumes across space and time for any given city. So if you look to the left side figure, that is showing about 14 automated traffic recorders in Denver, and you have complete information on volumes for 24 hours a day just in those 14 locations. Where we want to go with this ubiquitous volume estimation methodology is what you see to the right, which shows a heat map on different roadway segments. This is major freeways and highways within Denver, of what volumes are expected in that time snapshot on all the roads in Colorado. Now, if you want to take a look at different hours of the day, that's possible too. So we are employing machine learning algorithms to combine information that's available from the cities with probe vehicle information from providers such as TomTom and Inrix to come up with ubiquitous volume estimation. Today's presentation distinctly consists of 3 different portions. I'll be talking about the first part, the freeway volume estimation, just to kind of brush everyone's memory on what has been done so far. Yi will cover the lower functional class roads. These results are hot off the press. We've been working on this just over the past few months and have seen pretty encouraging results on lower functional class roads. Here I want to emphasize that when we presented the previous analysis results to various state DOTs, one of the major concerns that floated up in all of our presentations is what happens with the lower functional class roads. That's where there is really no observability, not even to the scale of automated traffic recorders, which record 24-hour volumes. Most lower functional class roads only have 48-hour counts that vary across the year. Time permitting, we'll come to the last portion, which is the AADT volume estimation. We did not want to cover all of this in one go because it might take a significant portion of time. So if there is enough time towards the end, we'll touch on this a little bit. As Stan mentioned, this is a figure that we all like here, which embodies the work that we are trying to do. Calibration network on the top is the automated traffic volume recorder information that feeds in as input to the volume estimator. Several other inputs such as probe vehicle information, roadway characteristics like number of lanes, things like that, weather information like temperature, fog, precipitation, and some temporal information feed in as inputs to the volume estimator to essentially output hourly volumes across 24 hours of the day and across different days of the year. So the previous run of this looked at freeways and major highways within the state of Colorado, and we've tested 3 distinct machine learning algorithms to do this. random forest, gradient boosting method, and extreme gradient boost. All three methods gave similar results, more or less within the same intervals. As Stan was mentioning, if you look at the ETCR values in the third column in the table, they're right on the border of what is considered as very good in terms of the volume estimates being useful for practitioners. Below 10 is acceptable. Anything below 5 is actually pretty good. So we are right on the border of that. The median R-square values are also pretty good. We started with using the extreme gradient boost method, more so from a computational efficiency standpoint, that it gives similar results as the other two methods, but it does so in an order of magnitude less of time. It takes only 13 seconds as compared to 124 seconds for gradient boosting or 73 seconds for the random forest models. So this is what we've done previously. These results are validated. They've been presented at the last meeting. We took this as the cue to go one step deeper and go with the lower functional class volume estimation. That is what you'll be presenting next.
Okay, thank you, Venu. So FHWA classed the roads to 7 categories. So in the previous study, in the freeway volume estimation, we include the interstate and other freeways. So in this study, we're going to focus on the low-class roads, which include the principal arterial, minor arterial, major collectors, minor collectors, and the local streets. So we have a table here to compare with some statistics of low-class roads with freeways. So if you look at the miles and lane miles and the VMT, so low-class roads covers almost dominate the road coverage in the road system. And also if you compare with the HPMS monitoring cycle, low-class roads has at least 6 years cycle, but a freeway has at least 3 years. And if you compare the monitoring method, almost all the low-class roads are monitored by short-term counts, while freeways have both ATRs and short-term counts. So the thing is that the low-class roads dominate the road system, but has lower observability. So that's why low-class roads is very important to have more observability, and we conduct studies on the volume estimation. And then here is the data we use to estimate the volumes. We use the 48-hour volume counts for the low-class road estimation, as opposed to only ATR stations for freeway estimations. We collect 35,000 observations out of 359 locations for low-class road study, but for freeways, we'll only have 14 locations and collect 52,000 observations at the ATR locations. So when you compare with the data collection period, we collect 9 months for the low-class roads, and we only have 3 months data for freeways. And the graph on the right side shows all the locations for data collection, and we randomly select 300 of those locations for model training, and set the other 59 locations aside for the testing after the model is built. As you can see, the blue dots shows the training locations, and the red dots shows the test locations. Okay, so here we talk about the methodology for model validation and test. So all the training locations were randomly and evenly divided into 10 groups. So for each iteration, we use 9 groups to train the data and use the one group to validate the model. So so we do this for 10 times until each group has been validated. Then we find the best model hyperparameter that yield the best estimation results, and use that hyperparameter to build a model using all the training data and test on the test data sets. As you can see in the graphs here, like for each iteration, we chose different groups for validation until all the groups have been validated in the 10 iterations. So here is the contrast of a volume distribution between low-class roads and the freeways. So 25% of the hourly volume are below 50 for those low-class roads, while on the freeways, only 1% of the hourly volume is lower than 100 vehicles per hour. The table shows the data characteristics by functional class. So as you can see, there are almost 80% of the observations were seen under principal and the minor arterials. And the volume on local streets are extremely low, and as well as the probe counts and the penetration rates. So this adds to more difficulty for the volume estimation for the low-class roads. And here shows all the input variables we used for the hourly volume estimation. We also highlight those not included that are different from the previous study. So we have TomTom chat data from the probes, this hourly average speed and counts. But in previous study we include the previous hours, but in this one we only include the present hour. And we also include hourly weather information. In previous study, we used the daily weather information. So we also use road characteristics. We use road class, whether it's urban or not, and speed limits. We also include 2015 AADT and the longitude, latitude in this study, which did not include in previous study. We also have a temporal information like month, day of week, hour of day. So the input variables are, so for any segments on the road, if we have all those features, then we can use the model that we built to estimate the volume on any of those segments. So the method we're using for this estimation are machine learning. So machine learning is a subfield in the computer science that gives the computer the ability to learn from the data and recognize the hidden patterns. And the extreme gradient boost are the exactly model that we're using for this low volume roads estimation. So this is one of the most recent developed tree-based machine learning models, and has been successfully used for classification and regression predictive model problems. And these are the model evaluation criteria that we use for the volume estimation. We include the mean absolute percentage error, which is MAPE, and the R-squared. The metrics are from the previous study, and we also add two new metrics. One is error to maximum flow ratio, EMFR, and the mean absolute error. So this slide shows the results and the comparison with the linear model and the AADT-based method. So AADT-based method is a method that factors the AADT to hourly volume. So as you can see, machine learning made a huge progress in the volume estimation. It performs way more better than a linear model and the AADT-based method. So the MAPE is about 50%. That's because we included all those extreme low volume, which makes the denominator really low in the calculation of MAPE. So then we further look at the MAPE and the error to maximum flow ratio for 20 vehicles per hour. Then you see MAPE is about 30%, and the error to maximum flow ratio is about 10% for those volumes larger than 20 vehicles per hour. So to further find the results, we need to look at the accuracy in the volume range. So we plot the MAPE for all different volume ranges with a beam size of 50 vehicles per hour. In order to interpret this figure here, we need to divide them to two parts. So if we look at the volume larger than 300 vehicles per hour, which is marked by the red color, and you can see the MAPE is really low and is stable. Most of the MAPE is around 15% to 20%. So then we look at the volume less than 300 vehicles per hour, which marked as a green color. And you can see the MAPE is high, but I would say the model is still good. Because if we look closely and take a look at the MAE and the error to maximum flow ratio for this volume range, you will see the MAE is really low. For volume less than 50, the MAE is around 10 vehicles per hour, and even for volume between 250 and 300, the volume the MAE is less than 100. Then if we look at the error to maximum flow ratio, most of the bars, the numbers are lower than 15%, I would say. So yeah, I would say the model is still good if you look at the those two metrics, because when the volume is extremely low, say the volume is around 5, then your prediction is like 25, then the MAPE would be 200%. So that's why for those extremely low volumes, the MAPE is high, but the other metrics is very low. So we also plot the predicted volume versus the actual observation in randomly selected 4 locations at 4 different types. So as you can see from the 4 plots, the observed and the predicted volume, they are in close agreement, and the machine learning can capture the general trend of the volume variation. So if we compare with principal arterial and the local streets, and you can see the MAPE is between 35% to 40%, but the MAE for local streets is really low. It's about 3, but for principal arterial is about 70. So which means for those low volume streets, even though the MAPE is high, but the MAE could be really low, and the model still performs really good. Then we also did the residual analysis. We plot the predicted volume and the actual volume on the left side of the figure. So the ideal case is that all points would be on the red line. So in this study, we can see all dots are still clustering around the red line, and if we do the linear regression, you can see the slope is 0.98, which shows that model is well fitted and is not biased. And we also plot the residue and the volume in the right side of the figure, and we also plot the mean error, not the mean absolute error. So it's a mean error, which shows if it's 0, then shows the volume is not biased. So we did this for different ranges of volume, and you can see from 0 to around 1,800 vehicles per hour, the mean error is very close to the red line, 0. When it's beyond 1,800, the model would underestimate the volume a little bit, because machine learning are really good at learning from data. We have a lot of observations from the low volume range. So the machine learning would use the experience learned from those low volume data to estimate the volume at the higher range. As you can see from the graph, there's not too many observations for those higher volumes. That's one of the reasons we don't have a sufficient observation in this range. And that's the same issue we had in our previous study. So the good thing about the XGBoost is that it can output the variable importance during the prediction process. So as you can see in this graph, we'll see hour, temperature, speed, probe count, GPS location, and the AADT are the most important variables for volume estimation in the lower class roads. And now we can see that machine learning works for lower class roads volume estimation, and like XGBoost are promising tools for hourly volume estimation in the future. And the model performs well for all ranges of volume, even for extreme low volume. If you look at the mean absolute error and the not MAPE, because those extremely low volume would increase the MAPE since they have a really low, small denominator in the calculation. So we tend to underestimate the higher volume because of the lack of sufficient observations in those volume ranges. We find that temperature, hour of day, GPS location, and the probe counts are significant. But the probe counts are not as significant as in freeway volume estimation. So now we are open to any questions.
Yeah, I think we'll pause here while everything's fresh in our head and also give Joanna a chance to swap slide decks for our next presenter. If there are any questions from those listening, please unmute your mics for the next minute or two. We'll take questions or clarifications. We'll also have time at the end for discussion. So are there any questions currently? Well, Yi and Venu, I think you did an awesome job presenting all that information so well that everyone's on board with what we've got. I'm sure we'll have questions later. Next up, we have University of Maryland presenting their work. They are working with a data set from Florida that got totally processed in time for the steering committee meeting, and Kaveh will be presenting the results from the large team of researchers there. Kaveh, the floor is yours.
Thanks, Stan, and good morning, good afternoon, everyone. Yeah, as Stan mentioned, in this presentation, we briefly present the results that we got for two new data sets that we obtained from INRIX late in 2016. Basically, Florida and New Hampshire data sets are two states that we've focused on so far. The two colleagues of mine who worked on this analysis, Przemysław Sekula and Zach Vanderlaan, they did most of the analytic work, and I have to give them credit for the great job that they did. I'm just here to present the results of their work. So basically, as an overview for this presentation, we are very excited that we want to share with you results of scaling the process to a statewide estimation. I'm going to get into details. Previously, we were focusing on estimating volumes only at ATR locations. Now we managed to scale this to the very large state, all TMC segments every hour of the 3 months of data that we had. that's a big accomplishment that we're excited about, and we have results, initial results to show you, and to show that the process is working, and the results that we're getting are really good in terms of quality and accuracy. Also, I'm going to briefly talk about the New Hampshire analysis we've done so far. We haven't got into the model development yet, but I'm going to briefly talk about the data set that we received and what's in there. I believe Stan is going to talk about next steps, and then we can entertain questions and answers. So previously, for those of you who probably need to get a refreshment on what we've done so far in this project, everything that we presented before was focused on 4 months data from Maryland that we received from INRIX. It belonged to 2015, fairly old data. We managed to develop a neural network model, machine learning type model that would spit out volume estimates at 45 ATR locations every hour of that 4 month period. And the result of that analysis led us to get fairly good results. The median of MAPE that we got was about 23%, and the error to capacity ratio was in the range of 4 to 7%. And one big takeaway that we got from that analysis was that estimation accuracy depends on probe penetration rate. So wherever and whenever we had more probes, the accuracy of our estimate was higher, and vice versa. But we were limited to ATR locations because preparing data was very difficult, and it still is. But over the course of time and shifting to new tools and new methodologies, we managed to overcome that problem for the new 2 data sets. So right now we're focused on, as I said, Florida. We have data from Q4 2016, and for New Hampshire we have data for Q3 of 2017, and both data sets are from INRIX. For Florida, we have developed the model based on data that we got from 173 ATR locations. And as I said, we applied these statewide. The INRIX data that we got was a snap to XT segmentation, and as such, if we want to go statewide, there are almost 20,000 TMC segments in the state of Florida alone. So we need to prepare the features and input data for all 20,000 TMC segments for a 3 month period. So that was the bulk of the work that needed to be done to do the statewide estimation. We will repeat the same process for New Hampshire now that we have the results for Florida, and we are pretty sure that the process that we're doing is correct and doable. Moving on to the next slide. Okay, let's focus on Florida. This slide gives you some statistics on how Florida data set compares to our previous data set, our Maryland data set. So in Florida, we are dealing with almost 75 million trips and 3.4 billion waypoints. While in Maryland, we were dealing with only 20 million trips and 1.4 billion waypoints, which basically tells us the Florida data set is almost 3 times as big as Maryland data set. The penetration rate that we're getting for Florida is about 2.1% in terms of the median. Slightly above 2%. In Maryland was slightly below 2%, so still we are in the same ballpark, so to speak. And in this case, for Florida, the waypoints were already a snap to XD segmentation, which was a big assistance, big help for us. In the case of Maryland, we had to do the snapping ourselves, and in the process, we had to go through a lot of hoops to accomplish that initial task. It has, its own advantages and also disadvantages. That's a question that needs a lot of time to go through to provide more detail and background on which one is more preferable. But we are happy with getting the data that's already a snap to the XD segments. In terms of the composition of the data, the pie chart in the middle of the slide indicates that more than half of the data, the trips, are coming from cars and light-duty trucks. Almost 30% of the trip data is coming from medium-duty trucks, and almost 16% are coming from heavy-duty trucks. Of course, that's just a brief summary of what is included in the GPS probe data from NREL. To do the estimation and to develop the models, we needed other data layers to sort of complement the GPS probes. So we used speed data, probe speed data that's coming from here, basically NPM RDS data. Then for road characteristics, we used TMC shapefiles from NPM RDS. And also, we needed OpenStreetMap for compilation and to take features from one segmentation to the other, so that we can have everything in terms of TMC segments, and we can move on and estimate the model and to produce the results for each TMC segment. The weather data is coming from permanent stations throughout the state, and also as another input, we are using the outcome of implementing TTI's methodology, which takes basically AADTs as an input, and after going through a rigorous process of combining that with other layers of information, speeds and whatnot, you get estimates of hourly volumes for each TMC segment. So that's one of the other inputs that we are using in our model. Of course, for each ATR station, we needed the counts. We received that data from Florida DOT, and we are thankful for that. This information is used for model training and evaluation, and also for estimating the probe penetration rates. The map on the slide shows the location of ATR stations throughout the Florida, and the coloring and the orientation of the triangles indicate the estimated penetration rate at the location of the ATR station, and also the direction of movement at that location. So as you see, these triangles either are pointing east or west or north or south, and that's an indication of the direction of travel. Again, darker blue shows lower penetration rates, and as you get to yellowish and lighter colors and red, it's indicator of higher penetration rates. And as you see the box and whisker plot next to the map indicates the range of the observed penetration rates, with a median around 2%. Okay, in terms of modeling, after all that input data layers were prepared, we used the dense artificial neural network. And by dense, I mean every neuron in a layer of the neural network was fully connected to all the other neurons in the next layer. So there is no attempt to reduce the size of the neural network or anything. It's just a basic implementation of artificial neural network that we tried for this modeling exercise. We approached this using cross-validation. So as I said, we had 173 ATR stations throughout the state. At every iteration, we put aside data from one station, and we calibrated and estimated the model on the data from the remaining 172 stations, and then we repeated this process 173 times. Then the results that we report is a comparison of predictions with the given ATR volumes, and based on that comparison, we generate metrics that we're going to report in the following slide. In general, when you plot the real volumes against estimates, we got, as you see in the graph to the right of the slide, there is a good good correspondence between the two, actually, and everything is close to 45-degree line, as it should be. So in general, it's an indicator of good performance in the part of the model. As you see, there is more density around the 45-degree line, as is shown by darker colors. Okay, as a summary of the results that we got for Florida, if you look at the tables, overall, the R-square that we got for Florida, this is the median of R-squares. It's about 0.83. The MAPE is 25%. Error to maximum flow ratio is 7%. And when you look at the breakdown on different road classes, because we scale this to all the TMC segments in the state. It includes freeways and arterials and other type of roads. So based on the information that we had in the TMC segment definitions, in terms of freeways in Florida, the R-square is 0.86. The MAPE is 21%, and error to maximum flow ratio is 6%, which is very comparable to what we got from modeling on Maryland data set. So they are very close, and it's very interesting. It shows that there is consistency and sort of stability in the results, even if we are looking at two different data sets for two different states, different time periods. It's very exciting that the results are showing a stable performance and consistent performance. So for Maryland, we had also 0.86 as R-square, 23 as MAPE, and 7% as EMFR. When you go down the functional road classification in terms of for principal arterials or FRC2, the R-squares dropped just a little bit, 0.82 is what we got. The MAPE increases to 26%, and EMFR slightly increases to 7%. For major and minor arterials, FRC 3 and 4, R-square is 0.83, MAPE is 33%, and EMFR is 7%. We see, it's clearly shown here that going down the road class table, the R-square gets a hit slight hit. MAPE, on the other hand, shows some rapid changes, but EMFR is pretty much stable. It stays in the same range, 6% to 7%, and that's very interesting. The table at the bottom of the slide also indicates the performance in terms of the hourly volume or vehicle per hour that's observed on each segment and each hour during that 3 months period that we looked at this data. So if actual vehicle per hour, the volume is below 1,000, then R square is 0.81, MAPE is 29%, EMFR is 7%, and as the hourly volume increases to more than 3,000 vehicles per hour, R square improves to 0.87%, MAPE goes down to 19%, and EMFR, again, is a stable around 6 to 7%. So again, with increasing volume, the R square and MAPE show more improvements as is expected. Some comments on this analysis and the results that we got. Obviously, determining the capacity of roads at a scale, given the available data, is a little bit tricky. Because to do that, to determine capacity, you need a number of lanes, you need for sure, and exactly what kind of road you're dealing with, whether it's a freeway, arterial, and so on, and that classification in some cases is not clearly defined, and probably some of the data that's available is not very accurate. So we focus in reporting the results. We focus on maximum flow rather than theoretical capacity, but noting that theoretical capacity usually is higher than maximum flow. So it's interesting to note that usually if you go with ETCR or theoretical capacity, probably you get even better performance in terms of percentage. So what we are reporting here, EMFR, probably is higher than the estimated ETCR. If you go back to our documentations and error measure definitions, you'll see the differences there. But overall, 6 to 7% performance in terms of EMFR probably correlates with maybe 4 or 5% performance in terms of ETCR, which puts us within the acceptable range for this type of data. But still, even though the results are overall showing good performance in terms of accuracy, there are still some challenges remaining with low volume roads. For instance, in this case, there are 7 locations that have 0 observed GPS counts for the whole duration of 3 months that we had data for. So these kind of situations have to dealt with differently and probably need more attention. Moving on to the next one. Okay. Here I have an animation of the results. So in one shot, you can see the Joanna. I'm not sure if I can get it to run from here. And if you can run the animation.
I'm not sure that the animation.
Oh, it's not working?
No.
Oh, okay.
I don't think so.
Well, anyways, we were trying to show, if you take a step back and look at the whole estate, all TMC segments, and look at the the progress of time, how the estimates would look like, in terms of the consistency and what would one expect, and it's in line with the expectation. Basically, if you look at it, you will see higher volumes in metropolitan areas and along the major corridors in the state, and also during the day, as you go through the peak hours in the morning and in the afternoon, you will see things that segments that would light up and show higher volumes. So we just wanted to show that that overall picture here, and to show that we have managed to do the estimates or get the estimates for all 20,000 TMC segments for all 3 months. In this slide, we wanted to show the performance at one particular ATR station, and the reason that we focus on this station, which was located near the Tampa Bay area, was that its performance was very close to the median that we reported, about 8.82 R-square performance that we reported for the whole estate. Probably we can't show it here in terms of animation, but as you see on the graphs to the left, the predicted estimates are following the actual count values fairly good, and it picks up the peaks and troughs of the graph, and we're showing that for both directions of movement at that particular ATR location. That was, what I told you so far was focused on Florida data set. This single slide summarizes what we've done so far and what we've seen in New Hampshire data set. While for Maryland, again, we are comparing this with what we saw in Maryland. 20 million trips and 1.4 billion waypoints that we had in Maryland. If you compare that with 7 million trips and about 600 million waypoints that's included in the New Hampshire data set, you get the point. With Florida, we were looking at a new data set that was almost 3 times Maryland. With New Hampshire, we're looking at a data set that's almost 1/3 of Maryland data set. So we have two different examples to work with. Again, for New Hampshire, the data is a snap to XD segmentation, which is a good starting point for us. And also, we ran into this problem that when you look at the result of a snapping, almost 70% of waypoints that are snapped to XD segmentation. In this data set, those points, those segments fall outside of the boundaries of New Hampshire. And at the beginning, we were very confused, and we were scratching our head why this is happening. But based on the process that NREX adopts to report the data, every trip that has at least one waypoint inside the estate has been included in this data set. But it seems we have a lot of trips going from Massachusetts to Maine through New Hampshire and vice versa that are reported as part of New Hampshire data set. They basically go through New Hampshire to get to metropolitan areas like Boston, for instance. So that's one major finding that we had so far. Again, in terms of composition of the data, about 46%, a little bit less than half of the data is coming from cars and light-duty trucks. About 36% come from medium-duty trucks, and about 18% is coming from heavy-duty trucks. So that's where we are with New Hampshire. We haven't done the modeling yet, but we are working on it. Hopefully, for the next presentation, we have results for New Hampshire as well. This is our contact information. Me and the two colleagues who worked on the analytics of this set of slides and results that we have so far for Florida and New Hampshire. We would be happy to answer any questions or listen to your comments regarding this and overall anything related to this project. Thank you.
Thank you, Kaveh. We're going to pause again probably for 30 to 60 seconds to give Joanna a chance to change the slide decks to see if anybody has any questions for Kaveh. Very pleased to see the Florida statewide analysis complete. We weren't anticipating that, so thank you. And thank you to all the speakers. We've stayed on pace. We do have a short presentation about some AADT work coming up next that Yi is going to present, kind of a very short presentation to give you the flavor. It's an area we're exploring. But I will pause another time to see if there's any immediate clarifications or questions for Kaveh. And hearing none, Yi, the floor is back to you.
Okay. So we'll take a first look at the AADT estimation for lower volume class roads. So these are very preliminary results that we have so far. And we use the same modeling techniques that we did for the hourly volume estimation for low functional class. And so we build a new model instead of aggregate the current hourly volume. And all the inputs are aggregated in the daily basis instead of hourly basis. And we use the daily average volume of the 48-hour counts as a AADT estimate. We didn't go through the whole complex equation that on the AADT book. So we just use this as a approximately ground truth for AADT. And this is just the first attempt, and we need a feedback from the audience. And at the end, we compare the estimate results with the daily volume of the 48-hour average. So here is the AADT distribution. For these data sets, we have about around 20% of the locations has a AADT less than 5,000. And here's the variables that we included and not included for this AADT estimation. So we included TomTom GPS data, which has daily average speed and the total daily probe counts. And we also have the road characteristics, road class, whether it's urban or not, speed limits, and longitude, latitude information. We did not include the hourly weather and the 2015 AADT information, and also the temporal information, because either there's no meaning to aggregate in an annually basis, or we don't want sheets with 2015 AADT information. So here are the results that we have so far. So the MAPE is about 33-34%, and this is really a significant process with machine learning when you compare with a previous study. So in the GATHER's 2007 study, they state that when it comes to AADT volume estimation on segments that without any volume information, the average error rate can reach to 100% or beyond. So it is really significant, and we compare with the linear regression, which is the most commonly used regression model. You can see the numbers. With machine learning models, it's about 34%, but for linear regression, the MAP reached to 165%. And we also did the same for the hourly volume estimation. We plot the residue. Here we plot the predicted and the actual AADT in the left side graph. We also did the linear regression for those points, and you can see the slope is 1. It's very close to the 45-degree line here, which shows that the model is well fitted and not biased. And then we look at the picture, the figure on the right side. Is a plot of the residue and the versus AADT, and we also plot the mean error of different range of AADT here. As you can see, for most of the time, the mean error align with the red line, which equals to 0, except there is one outlier here. We don't know what's going on there so far. We'll dig into more details maybe in the future. And here we build a new model without the probe data, which includes average speed and the probe counts. Then you will see the MAPE and the MAE increases significantly without those probe data as inputs. And also R-square has dropped. So this shows that the probe counts data are significant for the AADT estimation. And now come to sum up. Still, we show that machine learning approach is effective for AADT estimation, and we need to further verify the structure of the model. We just need to make sure that we are comparing and estimating the right thing. Also, probe count data are really important for the accuracy, and we also need some feedbacks from the audience. This is just some really preliminary results. We will do more in the future.
Thank you, Yi. A short presentation. We're able to put all the data pieces in place, make a few assumptions to make it work. And we think the results are representative, but it still needs some review and some touch-up to make sure that we got the right framework of the whole model. Joanne, if you can, switch back. I got a few wrap-up slides as far as trying to bring this all to a close and maybe initiate some discussion.
Mina, just a quick question. Was your question answered by Prajmek? Okay, thanks.
When perusing the two slide decks ahead of time, I think one of the best things to keep in mind right up front is we really got off the freeway in all of these studies. Even though Florida had a lot of freeway content in it, the vast expanse of ATRs in Florida definitely got off the FRC1 network. And if you just take a look, I brought this slide back from Yi's presentation at the volume distributions. This is coming from Colorado, but is representative anywhere. If you take a look at just FRC1 freeway type, you're on the right, and most of the volumes per hour is 1,000 or above. And if you go to the next FRC level and below, the principal arterials and below, the majority of the data is 1,000 vehicles per hour and below. So this really helped explore how this method would work once we get off the freeway. This is an attempt to sum up in one slide the first presentation we heard from Venu and Yi on the Colorado off-freeway results. I think the takeaways to remember is the approach using machine learning created stable, unbiased estimates even at the lower volume range. There are issues related to the metrics, particularly once you get below about 250, 300 vehicles per hour. Even though all the evidence shows the model stays stable, the metrics, particularly if you use the MAPE, may give you some problems because your denominator shrinks faster than your residual error. And so one of the takeaways on this was once you get below a certain threshold, we think that threshold is somewhere around 300 vehicles per hour, you may want you may continue to calculate MAPE, but really calculate on a different metric that may be more representative of the results, such as the mean absolute error. And the overall theme, and this is not just for the Colorado work, but across everything, performance is volume dependent. If you were to rank the roadway types, as shown here, principal and minor arterials, major collectors, and local streets, we did this when we were working with the probe data speed and volume, and we knew as you work down the functional class, it was more and more challenging to get quality data. It is somewhat true here as well, because as you go down these functional classes, you just get less and less volume, and as you get less and less volume, the statistics work against you. So if I were to put a qualitative measure, I think we're good to go on anything with the principal and minor arterials. Once you get into the major collectors, you get so consistently very low volumes, you have to be careful, and local streets are just very low volumes across the road. We think the modeling is stable, but in terms of MAPE, if you're looking to stay like below 30 or something like that, that'll be quite difficult. As a result of all this work, one of the things that's become a priority, since we are so volume dependent on accuracy, is we need to bring along some type of low volume filter or low volume flag or something when you run this estimator and says, hey, you're getting into a regime that we anticipate to be very low volume, and so the variance will be a little bit larger in proportion than you may expect. And I just brought forward some of the representative results to remind people of what that looked like. And I really like the chart on the lower left where we show principal arterial down to local streets, and what these numbers of a MAPE and a mean absolute error look like on a kind of visual eye check of how well it's performing in terms of how well it's able to reflect ground truth. If we go to the Florida results, I think we got many of the same takeaways. They had a lot of freeways, a lot of FRC1s, but an awful lot of principal arterials, major minor arterials 3 and 4. And similar to the work that we had there, they used artificial neural networks as opposed to some of the tree learning methods, but very stable results. They carried along this error to maximum flow ratio and it consistently stayed between 6 and 7%, which was good to see. That tends to be a more stable metric because you have the maximum observed flow in the denominator, so when you get into the very low volumes, the percentages don't escalate on you. And again, as said before, performance is volume dependent, as Kaveh did a great job. Kaveh, I brought forward this table mainly because I really like the second set, the hourly volume, 0 to 1,000, 1,000 to 2, 2 to 3. In comparing and contrasting these two results, it became evident that just, overall we need to get a consistent method of looking at accuracy within certain volume bins. And it should start probably the next iteration with NREL and UMD, whatever those volume bins are going to be, and then we can start taking the discussion to the next level according to the class of roadway and the expectation for accuracy. I threw this in there just to remind you how good is good enough. Once we're in all the statistical worlds, we use all these acronyms related to error metrics. Recall we had the error to capacity ratio and error to max flow ratio. They're very similar. It's just the max flow is a whole lot easier to measure than the theoretical capacity. And if it's 10% or less, it starts to become useful. 5% or less is our target. Across the board, we are approaching that 5%. Sometimes we can hit it and hit it consistently. But even in getting into the lower volumes, we're seeing that it's stably less than 10. When you get into this other one, the mean absolute percentage error is quite a popular metric, and we use that often because it's quite often used in traffic engineering. Again, it's very volume dependent. For high volume roads, we'd like to see it in the 10 to 15% range, and we think we're approaching that and consistently approaching it. The mid volume, 20 to 25%, and the low, extremely low volume, the 30 to 50%. And particularly when you get into the extremely low volume, the mean absolute error may be in a more appropriate metric. Now I throw these out there that these are not hard numbers derived from any data. These are numbers that were obtained by perusing the results from NREL and UMD over the past several iterations of analysis, and I invite your comment. I put it in contrast. I bring this MnDOT example. Sean Turner, who's collaborating with us, says, the best published literature on this has to do with the acceptability of AADT estimates that are volume dependent. And I throw that up just to show that also scales with absolute volume, and we need to be heading in that direction as well. The off-freeway takeaways in general, we're getting stable, unbiased estimates at low volumes. Performance is volume dependent. That's kind of a take on what we did before, breaking it into functional road classes. But realize that even in your upper classes of your principal arterials and minor arterials, there will be times where you get extremely low volumes in the middle of the night and things like that. So you still have to put those volume filters on there to understand it appropriately. I believe I should couch that appropriately. Looking at the whole body of work we've done, these accuracy targets that we're attempting to meet, they are being met. We're bringing value to the table and begin to start using some of this in some applications. We do need some consistent accuracy metrics by volume class. I think UMD and NREL, as well as the whole team, needs to step back, saying what have we learned over the past 8 to 12 months? Is there a natural framework for accuracy understanding that starts to emerge and start gravitating towards that? And likewise, kind of corollary to that, we need to get some confidence errors or error estimates into these volume estimates so that flags go off saying, hey, we're getting into some volume range. The expectation of accuracy is going to change slightly here. Initial AADT results. This is probably the freshest in your mind. Keep in mind that what we presented, we used for ground truth, we compared to the average of the 48-hour counts. These initial results are positive, but do require some iteration and more thought, and we invite anybody who's highly interested in that to provide that or have offline conversation. The only thing out there to compare it to is there was a MnDOT study about 12 months ago that the results were recently published a month or two ago, and we believe that our results compare favorably, and I chose my words carefully, believe, because we know that the frameworks, we just chose a framework that made sense, and we'd like to study the framework that the MnDOT used it, so we know it's not an apples-to-apples comparison, but the initial results are encouraging. So overall, stay tuned. Provide input, and we'd be interested in that. This last slide is where we're headed from here. I put a little gas gauge there and specifically did an internet search to show a quarter tank. I feel that's kind of where we're at with our research funding as well as the time horizon. We have a chance for one or more iterations on this analysis. And we're trying to target whatever we choose for the analysis, what do we want to do? At NREL, we know we want to take another shot at these AADT estimates once we talk to the community and get some feedback. We know UMD is going to extend their work to New Hampshire and get some good results there. So expect those two on our next steering committee meeting. The next bullet I have are candidate. That means if we had enough budget and enough time, we'd probably do all of these, but we don't. So we're going to prioritize them. For the technical work, we're going to look at low volume confidence flags or metrics. We also want to take a look at accuracy metrics indexed to abnormal special events. That's a fancy way of saying when the eclipse occurs in the Midwest, how well does this perform? Or during the inauguration in D.C., is this process still stable? We want to somehow put a weighting function on these air metrics to help identify things that are different than the norm and weighted accordingly as a way to build, well, both observability into how well it performs, and if it performs well, give people more confidence that this process works. We want to look at the relative importance of some of the input data. We're getting a better and better understanding every time we take another bite at the apple of analysis. It's becoming a little clearer, but there is still some muddiness there that we want to continue to work on. There is a continual issue, what happens when the volume exceeds the training data. We've seen it in both the NREL work and the UMD work, particularly on the extremely high volumes. The issue is you train a neural network or you train machine learning within a certain bounds, and you're starting to see some results that either right at that boundary layer or beyond that boundary layer. And one of the things we're learning is these machine learning techniques are not as robust as we may think that we've grown accustomed to in traditional modeling. So we'd like to put some filters on there to flag when we're outside of, say, the 5 to 95% input range and work with it that way. Error with respect to probe counts. This is another way to take a look at it. It's very similar to before. Take a look at the heart of this probe data is the number of observed probe vehicles, and can we begin to index the error according to that and learn something accordingly. On the AADT work, we want to continue the framework. Both look at high and low volumes, and I put PFS, that's an acronym for Pooled Fund Study. I know FHWA through Tin Jitang's office is interested in this, and they are considering or maybe even move forward on putting together a pooled fund study specifically for AADT estimation using these and similar techniques, basically so we don't have to expend as much time and effort collecting 48-hour and ATR counts around the nation. Another area is truck volumes, turning movements. I noted the comments from Mina Lockwood that we're aware that these probe data are very rich in many ways, depending on which vendors bring it to the table. And can we begin to take advantage of some of the medium and heavy-duty truck information embedded in this and actually break down these volume estimates into vehicle type, and if there's any promise there to do so with any accuracy. I throw all those out there because within the next 2 to 3 weeks we're gonna sit down between University of Maryland and National Renewable Energy Lab and say, okay, which parts of these are the most important, which parts of these is each entity going to take and try to get to the next level, and then we'll bring the results back to the steering committee. I'd like to thank you for the time. We've got 7 minutes left, which I must admit that was more time than I thought we would. There's a lot of material to cover. Joanne, I think I'm going to turn it back over to you with the time left, and if there's any questions people want to ask, now's the time to tune in and do so.
Thank you, Stan. And thank you to all our presenters today for those presentations. I know not only was that a lot of work, but I know you all worked really hard to try to fit that in so everyone, we could hear all the work that's been done in just those few months since our last meeting in November. I know Denise is also on the call at this point. Denise, I don't know if you wanted to say anything to the group?
Hi, Joanna. No, I was a late arrival, but it was always good stuff. I know they worked really hard, and the presentations went very well, so I'm very pleased. So thank you.
At this point, thank you, Denise. At this point, if anybody has any questions, and if you'd like to unmute your line, you can certainly ask, and we can open any of the presentations if we need to do so.
Hi, this is Port Authority of New York, New Jersey. Can you hear us?
Welcome. Yes.
Thank you. How comfortable are you with identifying type of vehicle, distinguishing between the large trucks and medium trucks and autos? Does the data really give you that?
Joanne, would you like me to take a first shot at that and have anybody pipe in?
That would be great, Stan. Thank you.
Okay. We collaborate with 3 data vendors in the I-95 Corridor Coalition, here, INRIX and TomTom. Each one brings significant value to the table, and as you work across them, each have come with a different flavor of data. One is more related to light-duty vehicles, cell phone oriented, and one particularly NREX working with UMD. If you look at their history and who they've grown out there, they tend to be richer in fleet data, and with the data sets that we say that we're working with from NREX come with data attributes, and those data attributes, one of them is what Kaveh showed, separating into medium, heavy-duty, and light-duty vehicles, and the associated percentages. To my knowledge, I don't know of anyone who's done any work trying to correlate or trying to turn models of volume estimates into that, but I think I'd lay the framework and turn it over to either Kaveh or Presmic, both of which have done. I know they've dove into that data to a layer deeper than I ever have as far as characterizing it, and see if they have any comments.
In general, I agree with you, Stan. Much of the data that's reported to us, it comes with that information. So the vendors, whoever aggregates this probe data sets, they receive that information that this data is coming from, for instance, a truck that's within this weight class. So that's given, but again, given the trajectory of the movements, where the trips start, where they end, you can always do data mining to probably get more insight into the type of vehicle that generated that trajectory. In my opinion, that's doable, but we haven't done that yet.
Steve, does that answer your question?
Yes, it still feels very much like a black box to me on that question. And I guess that's fine as long as we understand what we have and what we don't have.
Yeah, at the minimum, this is Kaveh. At the minimum, what this, at least the NREX data set that we've worked with, what it gives us is an understanding or an idea of general mix of fleet that this trajectory data is coming from. But specifically, if you want to focus on a specific class or weight class of vehicles, that's doable given the information that's already in the data set provided by the vendor. But what I'm saying is, it is possible to get even beyond that, and when you put this data with another layer of data, maybe a GIS or a map on top of each other, then you can do much more in terms of trajectory analysis, or to identify different types of trucks, the origins, destination. That's a different problem as opposed to what we are trying to deal with here.
Thank you.
Thank you.
Are there any other questions for any of our speakers today? Okay. As you can see on the screen, we're planning our next meeting for June, and look forward, all the steering committee members will receive information on that. The slides from all the presentations, as well as the recording of this meeting, will be posted on the Coalition website, and you'll receive links to that too. So again, we'd like to thank everyone for their participation today. And in the presentation, you'll of course find contact information for Kaveh, Denise, and Stan. And I believe we can get you information for the other speakers too if you have questions after the meeting. So thank you, and have a great day.